I've been foreshadowing it for a while, but today we're finally going to cover iterators. Iterators are a way to produce and perform operations on a sequence of values. We often use them with collections, so that we can perform the same operation on each item in a collection or reduce a collection to a single value. They're also often used implicitly in some forms of loop. As ever, this series is accompanied by a free book. Check the description for a link straight to this chapter. My name is Daniel. Welcome to Iris. Iterator is a trait that can be applied to any type and has a single required method. Next returns an option telling the caller there either is another item, some, or there isn't, none. Iterator also has 75 provided methods, which I think goes to show how incredibly versatile this trait is. We'll be talking about some of these methods, but it's well worth checking out the documentation to see what else is possible. While you'll usually get iterators from things like collections, it is possible to iterate through basically anything. To show the power of iterators, we're going to start by building an iterator from scratch, one that produces the Fibonacci sequence. The Fibonacci sequence is a sequence of numbers where each number is the sum of the previous two. Depending on whom you ask, the sequence either starts 1, 2, 1, 1, or 0, 1. Purists will say it's the former as Leonardo Fibonacci intended. Software engineers usually use the latter, but I'm difficult, so I'm going to stick mine in the middle because it really doesn't matter. Anyway, let's start by making a struct to store the state of the iterator. We'll need to know the previous number and the next number, and to keep it simple, we'll use a U8, so we'll only get numbers between 0 and 255. I've chosen to make next an option for reasons you'll see in a moment. Let's make a constructor so that the iterator always starts in a valid state. Moving on to implementing the iterator itself, the trait has an associated type, item, that describes the type returned by each call of the next method on the iterator. It's an associated type rather than a generic type, as it needs to be referenced a lot, but its type is dictated by the process used to create the iterator, so it isn't generic. To implement the next method, we'll need to temporarily store the current value of the next property. Because the value in the next property is an option, and the next method returns an option, we can use the question mark operator to either unwrap a sum variant or immediately return a none variant, depending on what's in there. If there is a none at this point, then we've reached the end of our sequence. Next, we'll update our internal states. Our new next value is the current value plus the previous one, and the previous becomes the old current. By using checked add here, we'll get an option that is none if the result is out of bounds. Finally, we return the stored current value, though we'll have to rewrap it in an option after unwrapping it earlier. So now we have our iterator type. We can now get each item off the iterator one at a time by calling the next method. You can see that each item in the sequence is wrapped in an option. When an iterator has no more items to provide, it will produce a none. The final number this iterator will produce is 233, after which we would overflow the U8 we've used to store the number. Just calling next, though, is pretty boring. No one wants to iterate through things by hand. What if we want to print out all the numbers in the Fibonacci sequence that fit inside of a U8? You can give an iterator to a for in loop and it will automatically unwrap the option for you. This code will print out each number on a new line. Once the loop hits a none, the loop ends. That's cool, but on its own it's still not very interesting. Iterators are designed to be chained. Those 75 provided methods I mentioned earlier allow you to do some exceptional tricks. For example, a list of Fibonacci numbers might be more useful if we knew what number in the sequence we're on. We can chain a method called enumerate, which will take the old iterator and give us a new one where each next now returns a tuple of u size t, where the t is the original item and the u size is the position. What's brilliant about this, though, is that when I say it takes the old iterator, it doesn't try to process every item in the iterator immediately. It merely takes ownership of it. When we call next on the iterator returned by enumerate, it calls next on the iterator being enumerated. Rust iterators are lazy, meaning they try to avoid doing any unnecessary work, just like me. Having built our own, hopefully you now have a vague understanding of how iterators work, but usually you'll get an iterator from a collection. As with most things in Rust, iterators, or specifically the items being iterated, can be thought of in 3 groups. All the collections we've discussed in the last video can give you an iterator in any of the following forms. Firstly, reference data. Often we don't need to own the data we're iterating over, it can be enough just to read it. All built-in collections have a method called iter, which returns an iterator type where the items are references to the data held in the collection. Here we have 2 variables that own the strings inside them. We move ownership of the variables into the vector. And then we create an iterator with the iter method, which will iterate over references that point to the data now owned by the vector. So calling next on the iterator gives us a reference, not the original data. This means the vector still owns the data. One thing to bear in mind is that if the collection contains references, then iter will give you an iterator that produces references to references. So if we change the original vector to reference the strings rather than take ownership, when we call next, we get a reference to a reference. Sometimes you need to edit things while iterating through them. Our second option allows us to do that. Itermute gives you an iterator of mutable references, and all of Rust's built-in collections support it, so long as the underlying collection is mutable itself. In this example, we'll use a vector of numbers, and as I mentioned, we need this vector to be mutable. We'll use a for-in loop like earlier using itermute. So here, n is a mutable reference to the value stored in the vector. By dereferencing n, we can add 10 to the original value. If we check the original vector now, we can see all values have increased by 10. Finally, you may want to take ownership of the underlying data, and that's where our third option comes in. Iter takes ownership of the collection and the data inside, meaning the collection will no longer be available. One place this is particularly useful though is when converting between types, either converting the items themselves or the entire collection. There is a trait called fromIterator that is implemented for types that can consume an iterator and populate themselves. This is almost always used with the collectIterator method, though you need to be explicit about what you're collecting into. You can do this either by typing the variable you're collecting into, or by using the turbofish operator, yes, that allows you to be explicit about the concrete types to fill in generics. In this example, we'll go back to our strings as they aren't copy. Instead of using a vector this time, we'll use a linked list and push our strings onto the end. This moves ownership from the variables into the linked list. To turn the linked list into a vector, we'll first convert the linked list into an iterator that owns the original data with into_iter. Then we'll collect that iterator into a vector. Because v is explicitly typed, Rust knows to use the fromIterator implementation for vector when calling collect. In this example, we've created a variable basically just to provide type information though. You can skip this step by using the turbofish operator, which looks like this. Going on what we've learned so far, what if you want to use owned data, but we need to keep the original collection, so into_iter is out of the question. There are 2 methods on Iterator for this purpose, copied and cloned. Each one takes the old iterator and returns a new iterator that applies the appropriate action lazily as next is called. Copied only works on iterators where the item is copy and will take the iterator and return a new iterator which returns each item copied. Cloned does the same thing for types that are clone. Beyond collections, there are other things that can be iterated through. Ranges, for example, are iterators. It's why you often see them used in for-in loops. But they implement all the same methods, so we can, for example, collect them just like any other iterator. You can make an infinitely repeating iterator of anything so long as it implements clone using std_iter_repeat. Because immutable references implement clone, we could use this function to repeat a reference to a string slice like hi. I said hi. Wait. Ooh, it literally never ends. Every time you call next, it just clones a new value. Okay, enough of that. We can also repeat existing iterators infinitely using a method on the iterator called cycle. Once the iterator has run out of items, instead of returning a none, it simply starts again. You can also create new iterators by combining other iterators with chain, although they do have to be of the same type. Many other types in Rust can also be broken down into iterators. The script for this video, for example, can be represented as one large string slice. You can break a string slice down by lines, chars, or bytes, all of which produce iterators. One common thing we might want to do is consume an iterator of numeric values to get some new value from it. A quick warning though, unlike some other operations we might perform on iterators which add some step that will be performed when we call next, methods that consume the iterator will actually try to process everything in the iterator, for example collect. This means that if you call them on an infinite iterator, like those created by repeat or cycle, your code will enter an infinite loop and never end. However, when that's not the case, there's some really useful mechanisms we can use. For iterators of items that implement the sum trait, for example numbers, the sum method will add all the items in the iterator together. You'll notice we have the turbofish operator again as we need to know what type to sum to. For iterators of items that implement the product trait, again like numbers, the product method will multiply all the items in the iterator together. It's worth noting that some surprising things implement sum and product, including blanket implementations for option t and result te, where t already implements the trait. When doing it this way though, for some reason the option needs to be owned, so here we've into-itted the collection as we don't need to use the collection afterward. Or, if we do need to keep the collection, because I32 is copy and copy is implemented for option where t is copy, we could chain iter with copied. I want to add another quick warning here. Sum and product use the basic add and multiply operators respectively. This can be problematic because there's no check to see if the result still fits inside the numeric type. For example, this is fine, and this will panic. But you won't know until runtime. Usually this won't be a problem as you'll likely be using number types with a lot of space, not U8, but we'll touch on a slower but safer way to get around this later. Anyway, carrying on with the maths. For iterators of items that implement ORD, you can use min to find the smallest value and max to find the largest value. Chars are ordered by their numeric value, so capitals come first, making H the smallest value in this example and W the largest. If you just want to know how many items there are, you can use count, which merely tells you how many items there are in the iterator. However, count consumes the iterator, meaning you can't use the iterator after using count. If the iterator implements exact size iterator though, and many iterators do, then you can use len instead. Not only does this not consume the iterator, it's almost always faster to get the same result. One of the most common uses for iterators is to process a set of items one at a time. There are a number of methods on the iterator trait that themselves return new iterators that are really helpful for this. In fact, it's common to chain multiple iterators together in this way. Let's start by looking at one of the simplest. You can take an iterator and exclude items based on the result of a predicate using filter. For example, we could take a range of numbers and filter out all of the odd numbers like this. If we were to look at the count of the iterators before and after the filter, you'll see they've changed. Now, I was going to point out that ideally we should use len, but that filter cannot return an exact size iterator. But to my surprise, exact size iterator isn't implemented for range inclusive either, but it is for range. So here's a quick edit to the code that does the same thing. Now we can use len on the range, which is much better. I don't know why range inclusive isn't exact size iterator. If you do, let me know in the comments, but I think it's a sign to prefer range over range inclusive. Hey, editor Daniel from the future here. Jumped over to my streaming setup to answer this one, even if it impacts my audience interaction. Cough, cough, like and subscribe and maybe leave a comment. While editing the video, I thought maybe I ought to just look this up, just in case the reason is obvious. I don't want to look too stupid. And the answer was, well, yeah, it is a bit obvious actually, but it also led me to some interesting revelations. So why can't range inclusive be exact size iterator? Well, it is sometimes. Exact size iterator is implemented for range inclusive where the numeric type is I8, I16, U8, and U16. Why those ones and not the others? Let's step back and think about what it does. Exact size iterator gives us a method, len, that returns a usize representing the total number of items in an iterator. If we take an example of U8 min to U8 max, that's the smallest representable number in a U8, which is 0, to the largest number representable in a U8, 255. The len includes 0, so the total number of items in the range is actually 256, which is one larger than can be represented in a U8. Len actually returns a usize, and the size of usize is the pointer width of the machine you're compiling for. If you compile for a 64-bit architecture, your usize is U64. If you compile for a 32-bit architecture, your usize is U32. Rust can compile for 64, 32, and 16-bit architectures, so in our example of range inclusive, it's fine for it to give us the answer of 256 because usize will always be bigger than U8. Hang on though, Rust can be compiled for 16-bit architecture, and range inclusive is exact size iterator for I16 and U16. Yeah, that's a mistake, one that can't be fixed. On 16-bit architecture, Rust will compile but give the wrong result for len on these sizes. It can't be fixed because it can never give the right answer in this situation, and we can't unimplement exact size iterator because that would be a breaking change on the standard library. So that's that then, right? Well, no. There was still something that was bugging me about this. You see, Rust has a feature called conditional compilation. We lightly touched on this in the tests video. It's how we stop tests being included in release code. You can choose what gets compiled based on what you're compiling for, and one of the things that you can create a condition for is pointer width. So I'm back to not being sure why range inclusive sizes that do have lengths that fit inside a usize don't have conditional support for exact size iterator. I also wonder if, were Rust to implement them, would it be a breaking change to fix I16 and U16 on 32 and 64-bit architectures? Still, going on what younger Daniel was saying, it definitely remains a reason to prefer range over range inclusive where possible, even if I don't think it communicates its meaning quite as well. Okay, I have a date with a librarian to go on, so back to that handsome guy from the past. Anyway, for obvious reasons, we don't know if an item is included or not before an item is processed by the predicate, so we don't get an exact size iterator back from the filter method, so we have to count each item afterwards. Another great way to process iterators one item at a time is to take that item and transform it in some way. We can pass the function into the map method that will receive the item and return a new value. If that value is of a different type, the iterator you get back will also be of that new type. If we start off with a range like this is an iterator where the item is of type I32. We can then use map to take the number and return the result of the format macro, and now we have an iterator where the item is of type string. Sometimes the process you apply to an item might itself result in an option, and rather than having an iterator of options, you may want to discard nones and unwrap OKs. This is where filter map is really handy. This range gives us every valid U8 number in sequence from smallest 0 to largest 255. Despite what we just discussed, this time it does have to be range inclusive. If we add 250 to each number, most of them will no longer fit inside of a U8. The checked add method found on most numeric types in Rust will return an option where the none variant represents an overflow. If we combine this with a filter map, all numbers that overflow will automatically be excluded because of the none, and all numbers in the sum variant are automatically unwrapped. That leaves us with these 6 numbers. This not only saves us from having to deal with doubly wrapped options from next, for example sum 255, but entirely removes the items from the iterator, meaning anything else we chain doesn't have to deal with it either. By comparison, if we just use a map, we'd have 256 options, 250 of which are none. Another way to reduce how many items we want to deal with in an iterator is by using take and skip. We can end an iterator early by only taking a certain number of items from it with take n, or we can skip over a number of items with skip n before resuming the iterator from that point. Like many iterator methods, we can chain skip and take for more interesting results, like skipping the first element and taking the next 4. Take can be particularly useful when working with infinite iterators. I want you to consider the output of the following program. An iterator method we used earlier, enumerate, allows us to add an index to our iterator by changing the type of the item t to a tuple of usize t. This can be really handy in combination with other iterator methods where the position in an iterator is important. Let's say we want to filter every other item out of a vec. We can do that by chaining together several of the iterator methods we've just learned. We'll take ownership of the data because we don't need the original vector after this. We'll enumerate the iterator so we get the index from the point we're at in the iterator onwards. Here we're at the start, but that might not always be the case. The index starts at 0, so by checking the modulo of the index, we can take every other item starting with the first. Filter doesn't change the data, only decides if it should be kept or not. This means we can ignore the original data inside this predicate. Since we no longer need the index after this, we can map the tuple and return just the data that we care about. Finally, we'll collect it and test the result. Anytime you see a filter and a map next to each other though, you might be able to abbreviate your code with filter map. Booleans can be turned into options with then sum, so this works, but in my opinion, you should always go with the code that's easiest to read, and it's up to you to decide what that is. Finally, there are 3 more consuming methods I want to cover for processing data. Fold and reduce consume iterators and return a single value by modifying that value for each item in the iterator. Fold lets you specify the initial value for the returned value, but reduce uses the first item in the iterator as the initial value and continues processing from the next item. Earlier, I mentioned some risk with sum and product and promised a slower but safer way to do the same thing. So let's try doing that with fold. It takes 2 parameters, the first being the initial value and the second being a closure which also takes 2 parameters. We'll use an option with a 0 for the initial value, which is why we can't use reduce in this specific case. For the closure, I'll usually stick to calling the parameters acc and cur, representing the accumulated value, which starts as our initial value, and the current value, which is our current item in the iterator. This closure will be called for every item in the iterator and returns the next accumulated value. We're simply going to add the values together. Our accumulated value is an option, and we only need to add if it's a sum variant. We can use and then to get inside the option if it's a sum, and we'll use the same checked add to increase the value. This maps our option to another option that comes out of checked add, so we don't need to do anything else before returning from the closure. That said, there's actually a better way to provide this functionality. The way we've built this, once we hit our first none, we know the answer is going to be none, yet we continue processing items. Thankfully, there's a method designed exactly for this, tryfold. Not only will it stop iterating on its first none, potentially ending very early, but because it knows we're dealing with options, it'll automatically unwrap our accumulated option for us, making this code much simpler. The last consuming method I wanted to talk about is for each. It lets you do something with each item in the iterator without returning anything. The simplest example might be if we went back to our Fibonacci sequence. Instead of printing the value in a loop, we can do it in for each. The lack of return value might feel like it rather limits the usefulness of this method. However, it can be useful when doing things like sending data somewhere else, for example, across threads, which we'll be looking at in the next video. There are a few more traits you may want to be aware of when making your own iterators or consuming others. Into iterator can be implemented on any type that can be turned into an iterator. I see what they did there. One place you might find yourself using it is on new types, or types where the most important data inside is represented as some kind of collection. Let's say we have a new type albums that contains a vector of album. In our domain logic, it might make sense that we can start a new collection of albums and add an album to it by buying it. So we can populate an album struct like this. If we were to implement into Iterator for albums, there are two important associated types that we need to specify. Item is easy, that'll be our album type. Into iter is the name of the type that is the iterator that will be returned. Remember back at the start of the video, we created a Fibonacci iterator. Our struct Fibonacci was an iterator type. What the trait is actually asking us for here is the data type that will manage the iteration process for us. We're using a vec internally, and vec has a generic iterator struct it uses when you turn a vec into an iterator. So we can just use that, filling in the generic part with our item type. All we need to do in our case then is return the result of calling vecs into iter method. Once we've done that, turning our albums type into an iterator of album is trivial. This code turns our albums collection into a list of artists. But what if we want to go back to having our albums type again? From iterator allows you to turn an iterator into another type, usually through the collect method of an iterator. In our case, again, we could really just lean into the existence of vec types utilities, but you could also rely on the struct's own implementation to do the same thing, usually just by looping through the iterator. Now we can create our album struct from any iterator of album. Finally, the last two iterator traits you should be aware of are double-ended iterator and exact size iterator. We could implement these for our album type, but we'd really just be wrapping vec, so I'll give some more direct examples. We've spoken about exact size iterator. It can tell you the size of the iterator without consuming it using the len method. Double-ended iterator allows you to reverse the order of an iterator with rev. The iterators returned from all collections in the standard library are both of these. To my surprise, even the iter structs for linked list and binary heap are both double-ended iterator. I actually didn't expect that. First, I want to say a huge thank you to my Patreons. Your support for the channel so early on really helps. We've now covered all of what I'd describe as the core synchronous language features, at least I hope. Let me know if you think I've missed anything crucial. We're moving on to threads in the next video. We'll discuss what they are, why you'd use them, and some of the most important and useful tools to use when working with them. And if you've enjoyed the video, don't forget to like and subscribe. You'd be surprised how much of a positive impact that has for us creators. With that, I'll see you next time.